afternoon, everyone. My name is Amit. I'm from ThoughtWorks. I'm a developer and consultant. And I have with me Gnana Ganesh, who is my colleague. And today we are talking about an interesting topic, as Sabine has introduced, the safety compliance of REST libraries, which is an important topic and which came up in some of our talks, and panel discussion as well. So before we start, a bit about ThoughtWorks. ThoughtWorks is a global consulting and technology services company which works across the tech stacks as well as different domains. One of the key areas where we are working in is software-defined vehicles, and there we are working with automotive companies to build software for modern cars. So a quick overview of what we are planning to cover today. A bit of background about safety compliance. What are the qualification requirements for software components? Our approach for qualification of the core library of Rust, and overview of the code coverage for Rust. We'll delve a bit deeper in how this is relevant for qualification, and how can we approach code coverage for the Rust core library. Okay, so a bit of background. What is required? Okay, what is automotive safety compliance for automotive software? It is guided by a standard ISO 26262, which is for ensuring the functional safety, and it defines all the processes and methods and what documentary evidence you need to produce for ensuring the software that goes in vehicles is functionally safe. So taking a step back, if we look at when we are trying to develop an application for ECUs, car ECUs, what are the things you need to qualify? Yeah. The first thing is the tools, the compiler which builds your software. And thanks to Ferrous Systems, we have already a safety compliant Rust compiler, and that was released last year. And the next thing is the libraries. It could be standard libraries, as well as the libraries which might be coming from third parties, or you might be developing yourself. The libraries also need to be safety compliant. And finally, the application itself, which you are going to develop, which will implement the functionality, intended functionality for the ECU. Of course, when you think about the system as a whole, you will also need to ensure that all the software platform, the operating system, middleware, etc., all those also need to be qualified. But here we are talking about the application. Okay, so if we delve a bit deeper about what are the compliance requirements as per ISO 26262, there are three main things. One thing is the documentation. The documentation covers all it serves as a formal specification of the software component, how it is being used, what are the functional requirements. The second thing is, have you tested your software for requirements? That's requirement coverage, and that is defined as per the ISO 26262 Part 6. And finally, the structural code coverage. Again, that is also defined as per ISO 26262 Part 6. So what is our approach for qualification of core library? So one thing is, how can we produce the work products defined by the standard for compliance of the core library? And the second thing is, as the core library is part of this Rust compiler itself, it is going to evolve. It is not being developed by a single entity. We also need to figure out how this can be done in an incremental manner. What are the different tools and automation ideas we can bring in so that the compliance becomes a non-restrictive and automated process. And that's where we can expect some discussion happening tomorrow by our colleague Ganesh on continuous compliance. Right, so let's go one by one. How can we approach for documentation and requirements coverage? So as I mentioned, the Rust's core library is released as and packaged with the Rust compiler itself. And the standard documentation can be a guiding factor for defining the requirements in a formal manner. So what we want to achieve for core library is how can we define the requirements in a manner which are easily testable, and then we can also analyze the Rust code, the compiler code, the library code, which can be traced and related with the requirements which we are defining. And this will help us in bidirectional traceability as well as producing the requirements coverage document. So what do we mean by formal requirements, and why do we need to do that? Here's an example. So this is a simple function in Rust's option module, core library option module. It's sum and this is the standard documentation which we find in the core library documentation. All it does is it's just a one statement, returns true if the option is some value and the value inside of it matches a predicate function, right? And there are some examples. However, in order to make sure that there are enough unit tests in your library code which cover this requirement, we can break it down further and define in more simple testable requirements. So one approach we are taking is defining requirements like this. I don't want to read everything, but the same statement can be represented as 3 requirements. The function will return false if the option value is none. If there is some variant, this function will apply a predicate function, and the return value of that predicate will be returned as the value. And finally, the function takes the ownership of the option value what we are passing. So these are testable requirements. Of course, this is just an example, and as we go further, we may have to modify or adopt as per the ISO 266 requirements. Going further, let's talk about structural or code coverage. So as per standard, there are 3 different types of code coverage requirements depending on different functional safety levels. I don't want to delve much deeper into what are the functional safety levels, but when we are targeting most safety critical level, which is ASIL D, you need to have the MCDZ or modified condition and decision coverage. So 3 types of coverage are statement coverage, where every statement in the program has been, you want to make sure that your unit tests are written in such a way that every statement in the program has been invoked at least once. The branch coverage is about whenever there are conditions in the program, whenever there is branching happening in the code, you want to make sure that every decision in the program has taken all the possible outcomes so that you are not leaving any block untested. Modified condition and decision coverage goes a step further, where a decision can be made up of multiple smaller Boolean conditions. It is a composite condition where you use logical operators to combine multiple small conditions, and here you want to ensure that every subcondition, to say, has impact on the decision you are making. So this happens if you have certain conditions which don't have any impact on the branching decision, that means those are redundant, and as per ISO 262, this is not acceptable. So moving on, like how can we achieve this structural code coverage for core library? Although code coverage seems to be simple, but we are talking about core library, which is part of the core compiler, and this is where we landed into some challenges. And to cover those things in more detail, I will invite my colleague, Gnana.
So whatever we have seen so far is what are the different processes we require for ISO 262 qualification. So let's get into the details of how do we do it for structural coverage, right? So structural coverage is like we discussed, covers 3 different types of coverage. So it contains statement, branch, and MCDC coverage. So before seeing how do we generate structural code coverage for code library, let's take a slight detour and try to understand how the code coverage in Rust currently is. I think we also talked about LLVM coverage in one of the previous talks about tools. So, yeah, let's stay. Thank you. Okay. So these are the 2 different flags that we have in Rust, which gives you code coverage. One thing is called Z profile, and the second thing is C instrument coverage. So Z profile is based on GCC, and it is GCC compatible. And the second thing is LLVM based, and it is C instrument coverage. So in this talk, particularly, we will be focusing on the C instrument coverage flow. And this is how the typical flow looks like. So you see here that we have the source code at the left, and then you have the compiler, which has these 3 different phases. So you have the HAR, which is high-level intermediate representation, and then you have MIR, mid-level intermediate representation, and then LLVM IR. Then we give this to LLVM, and so we'll get an executable. So yeah, profiles is something that we will see. And then we have the GR curve, which is again a Rust-based tool. So finally, the report. So we'll go into this flow in detail. Let's take a simple example and walk through this flow, right? We have this source code where we have a function of isEven. Yeah, it's not optimized, but it gets an n and returns whether it is true or false, right? If we compile this particular function with the C instrument flag, let's see what happens at different stages. And nothing pretty much happens in HAR as visually, but it gets something in behind the scenes. So it verifies the type, and then it also checks borrow checking happens. And yeah, that is pretty much on HAR. So now we pass this code to the MIR, right? So this is something now it's not recognizable because MIR does lots of optimization. So there are different optimization levels as well. So based on that, you will get a different output. So this is probably a not optimized version. And you can see that there are a lot of things called counter ID, expression ID, and counter increment, right? So these are the codes that have been added as part of your C instrument coverage. So if you don't pass these flags, this metadata will not have been landed on your MIR. Since you added the C instrument coverage, this metadata is getting added to your MIR, and this keeps tracks of what are the different expressions you have. It assigns a counter and also increments whenever it gets executed. You can imagine the basic blocks. So previously we saw something called as BB0, BB1. If you can, maybe you can. I hope it's visible, right? The BB1 here, BB2 and BB3. So these are like basic blocks which has a single point of entry and a single point of exit. So that's what we saw in the previous slide. You can compare it to like a train, which each compartment is a basic block. It has a single point of entry, and then it can exit. Of course, the exit could be based on a condition, which means if you are if you meet certain condition, you would take a different branch, and if you don't meet a certain condition, you could take another branch. But of course, in trains, I don't think it's there. But yeah. So next, moving on to the LLVM IR, we have the same MIR is being now represented in LLVM IR. We still have the basic blocks, and now instead of counter increment, we have something called as atomic raw add, right? So this is the internal syntax of the LLVM IR that is get passed to the LLVM so that LLVM can process beyond this. And we also have the same basic blocks which is being converted to the LLVM IR. Yep. So one more thing to note here is we have this profiles. So profiles are nothing but, it contains raw profile data. So profile data is like what are the different counters you have and how do you track those counters. So this is this counters value and the mapping. So mapping means you have the source code, and how do we know which this counter maps to a particular value in your source code? So this is done with the help of the profiles, right? Yeah. Moving on to the executable, we pass this LLVM IR data to the LLVM, and then we get something called as executable. We get executable, but this executable is slightly different. It's not the typical. I mean, if you don't pass the C instrument coverage, we will get a non-instrumented executable. In this case, we get an instrumented executable. So this instrumented executable means nothing other than that we add some more metadata because of the C instrument coverage. So this data is also being stored as part of your executable, right? And one more thing, it also contains profiler runtime. So it's also called profiler built-ins. Profiler built-ins is comes along with LLVM. Yeah, and this profiler built-ins is responsible for creating the profiles which we saw. So what it does is it kinds of at runtime creates some memory in your system when the executable is running, and it initializes the counters, and then it will be able to increment the counter whenever you have whenever the count increment is happening, right? It keeps track of them, and then finally once the executable is done, it writes this data back to your file, which is profile again. Yeah, it's not human readable. We need tools to visualize it, see what is in there. And this report, I mean, this is not a report yet. That's why we need tools like grcurve or some other torplane, a lot of tools, different options here. We used grcurve. So grcurve has different output formats as well. You can use HTML, you can use lcurve. So this takes in your profiles, and then it can generate a human readable report out of that. So that is pretty much on the flow, right? Now let's get into the thing. So whatever we discussed so far is this. We have the app code, and then you have this profiler runtime. So you need profiler runtime. Your app code links to that. Sorry. And you have this core. So this core here is the Rust core library, which the profiler runtime depends on. It would have been not a problem in any other library, right? Any other project, because it's just another app code. But in case of libcore, it creates a cyclic dependency. So you have this core library, which links to the profiler runtime, and there is this profiler runtime, which again depends on core. So it creates a cyclic dependency, and we need to fix this, right? So there are, I think there should be multiple ways to fix this. So one thing, and one straightforward thing that we came up is add a new flag to the bootstrap. So bootstrap is the process of building the compiler. So it's a script. Currently it is initially it started with the Python script, but it also has the Rust internally, right? So we added this flag called -- coverage, and when you add this flag, you build a different version of the profiler built-ins. So you still build profiler built-ins, but that does not depend on core anymore. When you don't pass this flag, things work the same like it had been previously, right? So what it enables us is it gives us it kinds of breaks the cyclic dependency and gives a new profiler built-ins, which we can use for code coverage. Let's get into a bit detail in this particular approach. So in order to make this, first what we have done is, like, there is something called as optional dependency, where you can make your dependency optional. So we also introduced a couple of features. So you can see a default and a core feature. So by default, your core feature is enabled. So core feature here means that you need dependency of core and the dependency of compiler built-ins. One thing we haven't mentioned so far is that compiler built-ins also internally depends on core. So that's why we have made compiler built-ins also optional here. So because of the particular feature that we see in the slides, right? So there's Rusty dependency of standard, so it also depends on core. So that we have to make it optional as well. And yeah, if we build this with no default features, we can get rid of core dependency. You may ask that, is this not cause a problem? Yeah, it doesn't cause the problem or error in our case. So yeah. And we needed a build step for the bootstrap. So like I said previously, bootstrap is used to build your compiler build script. And there are different steps it has for each and every process that happens internally in building the compiler. And there are three different things here, right? So the first thing is to build your custom profiler runtime. So for that, we just pass this no default features in the process. So we create an rlib out of that. So that's what you see in this particular slide. So this is the build step actually, which has this profiler built in no core. And we create, at the end of this process, we have this version of profiler built-ins, which without core dependency. And then we need to do a couple of more things. So we need to let the compiler know that we are using this version of profiler built-ins and not the default one, right? For that, there are a couple of flags that you can use. There is this extern flag, --extern, which kind of helps you to link any custom library that you want. And we use that in this place. You can see here we have this extend flag, and then we use that with profiler built-ins no core. So that's any name you can give. And then we give the path to that particular library that you are passing. Finally, you give this Z-profile runtime. So this Z-profile runtime is a flag in this bootstrap process, which helps you to pass any other runtime apart from your default runtime, right? So we also, this kind of tells the compiler that we want this particular profiler runtime to use at the execution. Yep, so let's look at the demo of this quickly. It's recorded so that, yeah. Hope this is visible. It's small. Okay. You can see here this test. So this dash coverage flag is added as a flag to the test subcommand, right? It is not globally available. So whenever you run test and you pass this dash coverage, and then we are not including any documents at this point in time. So documents are excluded part of the coverage. And we pass this path library core, which we want to create test. By the way, this is how we are creating the test coverage for, we are running the bootstrap command here. The .x is the bootstrap command. That you can't, if you're not seeing cargo. It creates, so it first runs the test and it creates an executable which contains the profiles. Sorry, it contains the profiler built-ins. And when this executable is run, since it has profiler runtime as part of it, profiles will be created, which you can see here. And yeah, once the files are there, you can use tools like grcow, and there are other options here. LLVM cow is again directly from LLVM. grcow is just some nice tooling around that. So we have this generate coverage report command, subcommand to this run command, which we can use to run this particular tool. So we can run this and pass the so it looks for the files and creates report out of that, which is getting stored in this custom directory. And we can see the report of that. So this is actually the coverage report of core library that we have generated. So yeah, that is on this demo part. You can look at this particular code in the PRs in Ferrocene. We have a couple of PRs on Ferrocene so far. And on this point, I also would like to thank my colleague who is not here, Atri Sarkar, and also Pietro Chapang. Call out for you for helping us in this journey. Yeah. So if you ask us, it is done. No, we are starting the journey and we have done some things and we have to do a lot of things still. So yeah, If you have any questions, comments, you can reach out to us. And this shows the current status of structural code coverage in REST compiler. So statement coverage is there already. And there is a branch coverage PR, which is available in draft PR. And MCDC is started, and it has been started by people, and it is in progress by the REST community. So, yep, that's it.
Just to add, the initiative of qualifying core library is from Ferris Systems, as they have been working on qualifying Ferris in compiler. ThoughtWorks, we from ThoughtWorks are committed to bringing Rust in software-defined vehicles, and this is a great opportunity for us as well to collaborate with Ferris Systems and see how qualification for libraries work for Rust libraries. Thank you.
Thank you so much. We do have time for one question. Take it over here.
So thanks for the talk. So you, part of your job is to break out or convert the documentation of the core library into requirements. So how do you track changes to the core library so you don't repeat this requirements definition over and over? Like if the core library changes, how do you keep track of that?
Yes, and that is one of the big challenges and challenge for us as well, because the requirements are going to be derived from the standard documentation, and if at all, because Rust being open source project, if at all these requirements lead to some requirements on library itself, we can plan to recommend this to the standard. So this could, in turn out to be a two-way process. But at this moment, for Rust core library, the source of truth is going to be the standard itself. To your question of accommodating frequent changes in the library itself, what we may have to come up with a strategy or maybe some tools which can help us in defining, interpreting the description from the standard and translating those into testable requirements. But that is something which is not concrete yet. We need to work on that.
Okay, thank you so much, Amit and Gnana, for coming and joining and sharing your talk with us.
Thank you so much.